Hello and welcome to South Carolina Linux Users Groups. Sorry, he already started the stream, so I'm going to go ahead and start announcing. Hello, everybody, and welcome to South Carolina Linux Users Groups, the Upstate Carolina Linux Users Group and the Columbia Linux Users Group in Columbia. I want to welcome everybody for coming tonight. Sorry, the stream started. Tonight, I'm really excited. We've got Tim Fowler, who is a former member here in the Upstate. You're in. Where are you at now, Tim?
So I'm based out of St. Louis. No, so
St. Louis. I thought he was in St. Louis, but I didn't want to say that and be wrong. But so yeah, and he's going to be giving us a talk tonight on low Earth orbit satellites. I'm really kind of excited about that. I appreciate everyone coming out tonight. I would like to. I'm curious to know how you found out about us, because I did like a blitz of advertising, just announcing. So I'm curious to know what avenues actually worked. I think, I wanted to announce that next month we're having a really it's exciting to me, but I asked a former member here if he would talk about licensing, which, in retrospect, it's probably not that exciting of a topic, but I thought in light of what Red Hat's been doing with their source firewall or source wall, and what has happened to Terraform with HashiCorp going to the business software license, I thought that it'd be interesting to get a perspective from our friend David Nally, who's the director of open source strategy at Amazon Web Services, if anyone's heard of AWS. And his title is Consequences of Open Source's Next Era. Open source has one. It's now the de facto development methodology and I must mention AI. Some of the things that happened with there was a bug about a year or so ago. Anyway, so he should have a very interesting perspective as the AWS's open source strategy guy. So anyway, that's next month. So feel free to come back. I'd love to have you. And we have a live Jitsi. If you're in Columbia, they're at the library tonight. And Tim, I'll let you take it from here. Thanks for coming tonight.
Thanks, Jace. I did lose you a little bit. So if I cut in and out, just let me know in chat and I'll try to back up.
Okay.
Or anything like that. So thank you guys for having me. As Jay said, I was a member of the group back starting early 2012 or whatever like that. Moved away, but I still consider you guys family and home, and I love to come back to you guys every once in a while and share some stuff. So a couple of things, kind of disclaimers about this. First of all, I am not a rocket surgeon. I do not have a PhD in orbital mechanics, orbital environmentals, pretty much anything environmental or orbital, and I did not stay at a Holiday Inn Express last night. Everything that I'm talking about is really coming purely from a amateur's perspective, somebody that really started with 0 and has maybe reached like 1 on the scale of 100 or something like that. So let's keep that in mind. Also, a little bit of background for those of you that don't know me. I am an offensive security analyst by trade. I specialize in penetration testing, red teaming, things like that. I look through things from the lens of how can I break it? How can I hack it? Where are the vulnerabilities and things like that? And so this is kind of the approach that I took when I started on this journey about 6 months ago. And it really started with a conversation with a good friend of mine at a conference in Nashville. And he works in the satellite industry or in the space industry. And we just had some conversations. And the question is like, generically, like, can you hack a satellite? And the answer historically is yes. There are accounts of those events that's happened historically, things such as many of you probably aren't aware, the first malware in space was Stuxnet. It infected Iranian television satellite because it was running the same PLC that the Iranian nuclear facility in Natanz was running, and stuff like that. So we've seen these historical events take place within satellite as far as security and stuff. But it's like, okay, can you hack a satellite? Yes, but more specifically, it's like, can I hack a satellite? Like, can I use my skill set as an offensive security professional? Like, can I go and attack a satellite or learn about it or something like that? And then, like, okay, that's kind of an open-ended question. Like, is there any like, where do we go? So then the next question that came into my mind was, how hard is it to hack a satellite? I know that it's possible. I know I have certain skill sets, but like, where's the divide? Is it, this far, or is it this far? But I don't like going to jail. If anybody knows my story and kind of how I got started in offensive security, is like I started building home labs early on because I don't look good in orange jumpsuits, and I wanted a place to practice and learn safely. So anytime I take on a new project or a new endeavor, a research effort, I kind of goes like, hey, how can I do this? How can I learn about this in a safe way? So then the next question became, can I build a satellite to hack? And that's really where I kind of settled on, as the question is like, let me figure out how to answer this question, because I'm very much a hands-on person. And it's much easier for me to conceptualize things, internalize things when I'm able to do them. If I'm just reading research papers and explanations and things like that, it tends to go over my head, especially when we're talking about in the space industry with all the math and things like that. It's just overwhelming. So these questions started coming up. It actually was April 15th of this year. I was at B-Sides Nashville. And like most things that I do in my life, I went 0 to 100 immediately and started like diving in to the point when I was driving back from Nashville. I was literally using Siri to do research queries and stuff, and pull up topics and give me some information, some background, because like, you don't know what you don't know. And there's a lot of assumptions that we will make about space. There's probably some assumptions that you all are already making. And I'll just go ahead and tell you, most of them are wrong. All of mine were wrong. But they were wrong for reasons that I couldn't even imagine and are never thought about. Because outside of the actual results of this research thus far and where it's headed, there was some big things that I learned along the way that really kind of changed how I approach my job, how I kind of come from things from a slightly different perspective, understanding that things aren't always as black and white, and there's always something kind of lurking under the surface that is acting as an inhibitor or something like that. So I jumped in full bore, like, so started on Saturday, April 15th, like, and within like the next 24 hours was just an absolute blitzkrieg of research on everything, like everything space related, everything satellite related. And because I needed to figure out like how to weed out, like, okay, where am I going to start to focus? Like, I want to build something for the purpose of hacking. So I immediately knew, like, 2-ton satellites in geosynchronous orbit probably wasn't the best approach to me. So I was like, okay, how like, what's the smallest satellites? What are the things like stuff? So looking at here is a abridged version of everything I knew nothing
Hey,
about.
Tim?
Yes.
Tim?
Yeah.
Tim?
Yep. I'm here.
The last 10 seconds or so, we didn't catch all that.
Okay, cool. So I'll go back. Can you still see the slide?
Yes.
Okay, cool. So basically, here's a unexhaustive list or a bridge list of everything that I didn't know on April 15th and 16th. And it's basically satellites in general, what their makeups are, how they work, how the ground stations work, the constraints that which satellites operate in, none of the RF design. If it was Wi-Fi, I got it. Pretty good at breaking Wi-Fi. Outside of that, yep, completely clueless. PCP design, space systems data structure, just how incredibly hard it is to build something to orbit Earth. It is incredibly hard to build something that doesn't orbit Earth, but simulates that. It's even harder to do it in the real world, or out of the real world, specifically. So where do we get started? Like everything, went to Google or DuckDuckGo, or Bing, pick your choice. But just started doing a lot of searches, started saving a lot of data, and just started trying to kind of piece this thing together a little bit. Naturally, given the background that I have, I was definitely wanting to gravitate towards open source solutions that are out there. That's actually what was kind of the precursor to all this, was the conversation. Is like, all of this stuff is out there. There is a ton out there that's published by organizations like NASA and Ball Aerospace, and people that play in this game. That's their job. They're publishing this stuff. They're making resources out there. It's just a matter of like putting the pieces together in a way that makes sense. So some of the things that I looked at right out of the gate was OpenSat Kit, NASA's Core Flight System, which is an incredibly powerful flight software. It's modular, and I don't know the total number of satellites that have flown in space using Core Flight System, but it is significant. It is a significant percentage of them. Also, Cosmos. Cosmos was originally written by Ball Aerospace, and it's now been taken over by a new company called OpenC3, and we'll talk about them in a little bit. But this is a ground station solution. And then NASA also put this thing out called NOS3, which is the NASA Operational Simulator for Small Satellites. And it incorporates Cosmos, Core Flight System, a visualization program called 42 to be able to simulate orbits and stuff like that. I've got a screenshot here. So this is what NOS3 looks like. It runs in a VM. I think the VM's like Ubuntu 1804. It might even be 1604. I don't remember. I didn't play around with it a lot because, well, I kind of thought it was ugly, frankly, if I'm just being completely blunt. Like, this isn't very attractive. And one of the things that I wanted to do is, at the kind of conclusion of this research, I wanted to be able to make it so that other people could do the same stuff, that they could play around, that they could get involved, and get exposed to this stuff. And I was like, this stuff just isn't really super pretty. The answer to that is, it became abundantly clear as to why, is because they don't have time to make it look pretty. They're too busy doing complicated math and everything else like that. And so it's really not something that is a high priority. If you look at a lot of like flight systems and stuff, like it's very rudimentary. Does it do the job that it's designed to do? Yes. It doesn't necessarily have to look pretty. But this is, if you want to play, NOS3 is something that you can look at. And so like this is like how this whole thing started. But as I started to kind of filter down in what was accessible, what was available to me, what kind of options I had, I really settled on like this idea of a CubeSat. And a CubeSat actually has a definition. It's classified as a picosatellite. It is defined by its unit size, in the same way that we have rack units, like a 1U, 2U, 3U rack unit server. We have a 1U, 2U, 3U CubeSat, and it's fundamentally a 10 by 10 by 10 centimeter cube that weighs less than 1.33 kilograms. And there's some other additional constraints and limitations there, but for the most part, that is the standard. It was originally, the standard was published, I believe, in out of Cal Poly in 1999, and there's been a couple of revisions. And as recently as February of 2022 was the last one, but it was is a standardization that really helped radicalize space and really push this democratization of space forward, where for the longest time space was all about, it was nation state and the governments and the militaries and stuff like that. It was massive hundreds of millions of dollars of projects, and in some cases billions of dollars of projects, and it just wasn't accessible to anybody else. But CubeSats, along with the low reduced cost of technology, the reduced launch costs, which is also partly tied to CubeSats. One of the kind of benefits of CubeSats was this the ride sharing program. I call it Uber for space, but effectively, when you have a monolithic satellite payload or something like that. Let's say you've got a rocket that's got 2,000 tons of capacity, which is pretty small, but let's just say that, and you have 1.5 ton satellite that your customer is paying for. We have 500 500 kilograms or whatever of capacity left that's already been paid for by the primary customer. What if we pack a bunch of these little smaller satellites in that have this? We control the definition of them, so we know that they'll fit and stuff like that, and we can reduce or spread that launch cost to them. And that's where this ride sharing program, SpaceX is notorious for it. Rocket Labs is one that is a company that's all they do is ride sharing CubeSats, which is really cool, which has driven the cost way down. About 6 years ago, I think the average cost for a 1U satellite was about $160,000 just in the launch cost. Depending on timelines and stuff like that, it's a little bit hard to narrow down, but you could potentially launch a satellite in 2025 for $45,000, not counting the actual cost of the hardware. If SpaceX Starship becomes a successful program, some people believe that cost could get under $10,000 per unit, which is just absolutely incredible to be able to do that. But because of that, there's a proliferation of these CubeSats in orbit from research institutions, universities, but as well as just commercial endeavors and stuff, because CubeSats solve a lot of problems that organizations would face with larger projects. For one, they're just obviously cheaper to produce, cheaper to launch. They operate in low Earth orbit, which is nice because that's the cheapest to get to. Even if you're going to a higher orbit, you're going to stop off and have a little stay in low Earth orbit anyway. So if you can do as much of as possible in low Earth orbit, it makes sense to hang out there. They typically have fairly short lifespans or missions, typically less than a year. And that's mostly due to the constraints of size. You can't carry a lot of active navigate or maneuvering capabilities. If you have propulsion such as cold gas thrusters, you're very limited in that. So it's very difficult to overcome the gravitational effects, and eventually your orbit will decay. But it makes a lot more sense to send, in some cases, 5, 10, 200 CubeSats up to be able to cover the entire globe, depending on what your mission objective is and things like that, versus maybe like one monolithic satellite that has to go 35,000 kilometers above Earth. Extraordinary cost and stuff. You also have more resilient missions. The perfect example of this would be Starlink. Starlink is not CubeSats, but they're using this. It's the same kind of concept that's being applied there, is where they're using this constellation of satellites to be able to cover this entire Earth, but they're really cheap satellites. And if something happens, one of them gets hit by space debris, whatever, it's really not the end of Starlink. Like, they just send another one up. They're sending 21, 22 satellites up multiple times a week to build their constellation out. These small satellites are definitely where everything has moved and is going to continue to move. And so this is where I kind of honed in on this. But then I started looking at them like, well, how much does it cost to build a CubeSat? I was like, can I go buy? Very, very expensive. Still very cheap relative to other types of satellites, but commercially, about the cheapest I could get is about $90,000, which is still really super affordable. Relative, not to me, but I was like, okay, so the legitimate hardware is still crazy, crazy expensive. That's out of my league. Let's see if like there's other options and stuff. And I came across this YouTube series that's like building a CubeSat for less than $1,000. It's a fantastic series, except the guy never finished it, and it went over budget. Not surprised, but it was really, really well done. But so I kept looking, and I think when I came in, I heard somebody mention AMSAT. I may not have, but if I did, awesome, because we're about to talk about them. So I started doing some research, looking for solutions and stuff like that, and I stumbled across the AMSAT CubeSat simulator project, primarily authored by Alan Johnston. But there are multiple people involved, and I started looking at it, and I was like, it was instant. I'm like, this is where I'm going to start. They've laid all the groundwork out for me for what I want to do, for the most part. So it's like, let's dive in, let's look at this platform, and let's figure out what they have. I would encourage you guys to go look at this project. The documentation in the wiki, especially from an assembly perspective, primo. They do such a good job, and I'm just an absolutely huge fan. I've had a chance to talk to Alan a few times over email. Just absolutely wonderful. But so a breakdown of what this looks like is, so it's comprised of 3 PCB boards. It's run by the onboard computer is a Raspberry Pi Zero W. It includes voltage and current sensors using INA 219 sensors, a nickel metal hydroxide battery pack, necessary charger, boost converter to go to 5 volts, as well as a collection of sensors controlled by an Arduino on that top board. And I'm like, this is a great starting place for me. But it was less than perfect, because ultimately my goal, putting on my offensive security hat, is like, I want to mess with this. I want to play with this and make it do things. But the AMSAT CubeSat simulator it's a Sputnik, meaning it's only transmit only on approximately 433 megahertz, which is cool because the way they have it set up is absolutely fantastic. And if you're interested in radio, if you're a ham radio operator, you definitely need to go check out this, because they support all these different modes and things, and it's such a well done project. But the hardware was really where I was more interested in, not so much as the software stuff, because like I had my own ideas for that, but it's like, I need to figure out these issues. And so the satellites transmit only. The ground station solution that they have is receive only. It's like, how do we overcome these issues? And it's like, this was the thing that kept like just sticking in my head. How do I solve the TX-RX issue? Well, naturally, you jump in and get your ham radio license in 12 days. I actually don't recommend doing this for people, but I tend to go overboard. So we started on April 15th. By April 27th, I got my ham license, technician's license, which I didn't necessarily need, but it really kind of opened my eyes up and helped me understand, like, okay, so a lot of the stuff that we're dealing with here, because for instance, operating in the ISM bands, you're not, in normal communications aren't to be encrypted. There are a few exceptions to that, but satellite communications are something that can be encrypted in ISM bands. It's like, hey, that's actually really beneficial. Ultimately, I haven't used this for where I was headed, but I'm going to be circling back to this in the next couple of months, and we will be taking advantage of the benefits of having a ham radio license. But one thing that I do want to mention, according to the FCC, any broadcast from a satellite, you do not have to have a license to listen. If you can tune into the frequency, if you can demodulate the signal, you can listen in, you can look at the data. There's no restrictions to that. The only restrictions is transmission. And so for that, you would want to have your license and stuff, but also in a lot of cases, satellites are not operating in ISM bands. More research-based ones will, but they will actually buy license for specific frequencies and stuff like that. So you probably wouldn't be able to legally transmit to them anyway, but just something to take in a note. So next, I need to kind of define the requirements that I needed to kind of solve that RxTX problem and do it in a way that I could actually understand. Because remember, if you were early on, I didn't know any of this stuff. My experience with like Arduino and stuff was like turn on an LED, and that's pretty much it. Same thing with Raspberry Pis. I typically operate more server infrastructure and automation and stuff like that, not so much in this low level hardware kind of realm. So I needed the communications to be bidirectional. I knew based off the hardware that AMSAT CubeSat simulator was using, I had both SPI or I2C serial buses available to me. I technically could have done UART as well, but I figured it would be a little bit easier just to stick with those. A requirement that I had was I needed to easily be programmable in Python, which has been a bit of a contentious point, even with just the team of myself. But for the first iteration, I decided I wanted everything to as much as possible to be Python based, because I wanted it to be a little more accessible than some of the C stuff, and just be able to make it a little bit more rapid development I'm much stronger in Python. So I was like, do I want this to work, or do I want to spend all my time troubleshooting, all of these code issues and stuff? And so it's a little bit of a trade-off, but we said, all right, we're going to do Python to start with.
Oh no.
What happened, Jace?
I don't know. I guess Tim just dropped off. Hey, there he is.
Back.
Your mic. You start muted, by the way, Tim.
All right. Sorry about it. Not sure what happened.
Well, you dropped off the earth.
Well, yeah. Sorry, I was in orbit. My bad. As on the dark side, we're not going to get into that, just to all of the orbital mechanics of communication windows and everything like that. But I know about those now. So I'm not sure where I dropped off, but I was basically saying that I'd made the decision to do all of this initially in Python, and there will be more embedded C versions of things later, as things progress in this project stuff. But I need it to be small. The AMSAT CubeSat simulator has a little breakout section on the stem board that I needed to hopefully try to do, so I didn't have to jerry rig too much stuff. Long range capabilities would have been nice, and not 802.11 for just reasons. It doesn't stimulate very well into real world satellite communications. There's too much noise and things like that. So I decided to actually use LoRa. If you're not familiar with it, LoRa stands for long range. It's a wireless modulation primarily designed for IoT, but it worked out pretty well, in my opinion, because it's relatively cheap. Comparatively, you can do both SPI or I2C, depending on what module you have and stuff. Is fairly low power, which, while developing this, I wasn't super power conscious in terms of planning. It was always in the back of my mind of like, hey, I need to make sure I'm aware of what our power budgets are and stuff, because in the real world, in the orbit, power budget is everything. If you use more power than you can produce with your solar panels, your mission is over, effectively. And there's a lot of that goes into that. Some of the attacks that I've been able to simulate and stuff are actually around exhausting power resources, abusing the radios so that they go into basically transmit loops. For example, the module that you're seeing on screen here, it uses approximately 34 milliamps of power. in receive mode, and it's 120 in transmission mode. So if I can just get it to continuously transmit, we're using approximately 3x times of power, which means now I've got to figure out where that power is coming from to make up for those discrepancies. So this is what we went with. The awesome thing about it was the maximum bandwidth is approximately 61 kilobits per second, which you go, wow, that's awful. Yes, it's absolutely horrible, which is great for simulating satellite communications, where every packet has to be very strategically designed to have as much data as possible in it, nothing more, because you want to minimize the amount of time that you have to transmit. And so in this case, with the particular ones, radios that I went with, the RFM 95 LoRa modules, it happens to have a maximum packet size of 255 bytes, which was great to work with as a limitation of the FIFO buffer in the module. So I was like, all right, here's what we've got. This is what we're going to go with. So the next thing was to order some PCBs from AMSAT. They're like $35, I think, for a 3. I ordered a set of 2 of those. They came in very, very quickly and started piecing together the components is a little bit difficult. Supply chain issues, parts not available, just all kinds of little, quirks and stuff. And also you're dealing with components where you're not doing in large quantities, so the price can tend to be high, and trying to figure out appropriate replacements and stuff. But eventually we built the entire thing. And then we added the LoRa module over here on in the left image over here on the right side of the board, and it fit perfectly within those. And the original plan was like, hey, let's design a PCB that just has traces to the appropriate pins in this case we're communicating over SPI. That didn't. I just ran out of time, so we decided to just jerry rig it with jumper wires and solder, and it mostly worked. There was a couple of catastrophic issues, but for the most part, it does work. And so we solved that problem. I was like, okay, now I have a module on the satellite that I can control using Python library. Great. I now need to receive this information. A lot of times you would use something like an SDR or something like that, but LoRa, unfortunately, is a proprietary modulation. And so it's not something while you can see the data with an SDR or see the waveform or in the waterfall, you can't actually be able to decode the data, demodulate it and stuff. So you basically have to have the same thing on the other end. So me and my infinite wisdom, I was like, well, let's go design a custom PCB because this will be great. It was not great to start with. So I started off simple and just designed a PCB that uses a Raspberry Pi Pico running. Originally, it was MicroPython, but I had to switch to CircuitPython for some technical reasons later on. And then we just wired it to the RFM 95 LoRa module. This particular one is from Adafruit, which was really nice. But the problem is they run about like $25 to $30 a piece. So what you're looking at here is about $31 worth of hardware. And it's like, that's not like super exciting. Like that's not bad for what it is, but it's like, it doesn't really hit that mark for like, I want somebody else to be able to do this and do this a little bit easier and drive that cost down a little bit. So it's like, okay, we got this working. Let's now design an SMT surface mount device where the cost goes from like $25 to like $6 for the module. Plus a couple of passive resistors and capacitors, and then you still have the Pico. So it's like we designed this. Yep, it didn't work. Don't know why. Haven't been able to figure it out. Didn't waste my time. I was so excited when it came in, and I was like, yay! And yeah, it didn't work. Neither did the next one. Like I said, I didn't really know what I was doing with PCB design. A lot of late nights trying to figure this stuff out, learning. Eventually, I have a custom implementation with a Raspberry Pi Pico and a RFM 95 running, and it's receiving data. If you look down at the bottom in the little Cirrus shell, you'll see that it is actually getting data from the satellite. Hallelujah. This was an amazing moment. It was just, so much time went into this. So now it was time to write some software. But where do you start? Knowing that I wanted to have ground station control, bidirectional communication, I didn't think it was wise to write my own ground station solution. Mostly due to time constraints. I was trying to get this first phase of the project done by October, so that I could go to my company's security conference, Wild West Hacking Fest, and demonstrate this stuff. And so I was like, I gotta make some concessions somewhere. And so I found OpenC3 Cosmos, which is the newer version of Ball Aerospace's Cosmos. It looks so much better, in my opinion. It's well documented. They have an open source as well as an enterprise version. And I was like, this is great. This gives me the ability to send commands, receive data, but it is a very basic framework. It's a very powerful framework. But one of the things that kind of I struggled with early on was every single packet had to be well defined, such as a telemetry packet. It needs to have a telemetry ID. Every field, every byte. If you have a multi-value packet, such as voltages across all 6 axes, those have to be delimited in your packet definition, so that when it reads it in, it goes, no, hey, this is this voltage, this is this voltage, this is voltage. It was just so frustrating, because it's like I'm just not used to thinking in terms of individual bytes and stuff. Like I haven't had to do that since I was doing some shellcode and binary exploitation stuff, and it's just like, wow, okay, this stuff is actually kind of complicated. And then just like handling all the data, it's like, okay, everything's coming across as binary. We got to make sure everything decodes correctly, and we can't send random junk and stuff like that. But I finally got a integration using their documentation, which was absolutely, I was able to integrate the custom PCB LoRa board, and then start communicating with the satellite, which was absolutely fantastic. But everything didn't go quite according to plan. I realized that by design, LoRa is not a super reliable protocol. I consider it like it's effectively like UDP in a lot of cases. There are implementations that you can do, acknowledgements and things like that, but that effectively doubles your or halves your data rate, because now you're doing a send, an acknowledgement, and you're playing this TikTok kind of thing, back stuff. So one of the things I was experiencing was I was dropping packets randomly, and especially in large sequences. So I was like, okay, well, we'll just write this retransmission routine so that I can basically specify like, hey, what of the last set of packets that you've sent me, or the last file you've sent me, I did. And it was awesome and kind of funny at the same time, because I was like, the software did exactly what I wanted it to do, but it didn't only do what I wanted it to do. And that just goes to show just how incredibly hard it is, software in general. And it's even crazier on the space level. The thing that I can tell you is this exact vulnerability did exist in a software package that was flying in 2021 on a CubeSat. Because I was like, where did I get this idea of handling it this way? Yeah, it was an existing CubeSat project from a university. And so I was like, and I went back and looked at the code. I'm like, yep, they're vulnerable too. They decayed and burned up in the atmosphere, so it's really not a risk. But like, this is how simple problems can be in terms of a vulnerability perspective. If somebody was doing command fuzzing on this, it would have been very easy to identify this and actually take over. This is operating as root, and so the entire satellite could have been compromised at that point in time. But finally, after lots of effort, lots of work, we started getting things working good. Here you can see using on the right, we've got an SDR using GQRX. We're able to see the packet data coming in. We don't know what it is, but we can at least see it. And then in the middle is the actual CubeSat flight software that's running. And then on the far left is the packets that are being received. as well. It is working, and I was super excited about that. And so it's about this time I was like, okay, I'm gonna make it. I'm gonna hit this finish line. I'm gonna cross this. We're gonna have something. A platform that we can start hacking on. And I was like, I need to kind of like start thinking like how to not sell this because it's not a commercial product or anything like that, but it's like as far as a branding perspective, and everything has an acronym in the space industry. Every satellite means something or another. Or whatever like that. So I started just kind of thinking stuff, and one night I was messing around, and I finally came up with the name Ethos for the overall project, and it's just educational technologies for hacking orbital spacecraft. And there's a lot kind of under this umbrella, especially in the future, where things are headed, and we'll talk about that briefly at the end of like kind of where we're at now and where we're headed. But I think this is a video, maybe. I don't remember. Yeah, so here's a video. It's probably not going to show very well through the stream, but I'll just kind of give you an idea of what's happening. So this is in OpenC3 Cosmos. We're connecting to the serial to the hardware over serial, and all of this stuff is defined. And right now we haven't received any data from the satellite. We're going to switch over and run a single command from the satellite itself, just testing this transmission. What this is doing here is it is essentially taking an image file and chunking it up into 166 byte chunks, because when you base 64 encode it so that you have no like null bytes or anything like that, it comes out to roughly 232 bytes with all of the preambles and the header of value, telemetry IDs and stuff like that. That was basically the largest package we could do. And so then we send those over, and the ground station receives those, and then we're using the data processor or data extractor is what it's called within OpenC3. And it will generate a CSV file of all the packets that we just received, and wrote a decoding Python script to parse the CSV file, pull out the image data, and then recompile that into the actual image file. And we'll give it a second. Like I said, I don't know if you guys can see it. Hopefully you can, but you'll get to see the actual results.
Yeah, it's good.
Okay. It's almost done. It looks like it's hung on my end. Oh, yep, there it goes. And so then there's a little image of my stuffed otter that sits on my desk, because one of the things is the satellite platform does have a camera on it that's part of the payload capabilities and stuff, and I wanted to be able to leverage that. Oh, I guess that's in there twice. So this is kind of what the final version of the project as of in October was. Prior to going out to Wild West Hacking Fest, we had 2 CubeSats built. Actually had 2 different labs that we were going to run. But I ended up running only a single lab in parallel, just because there's a huge educational problem here. That if you're not familiar with the terminology, if you're not familiar with the technology and how the data flows and stuff like that, there's a pretty steep learning curve. And it's very difficult to have somebody sit down and it's like, okay, I want you to go through this 50-page document in 20 minutes of how to do it. Like I could click through it in 8 minutes, but because I know this and stuff. So we went with a simpler lab, but people had a lot of fun with it. And we were able to turn it and integrate it into part of the CTF challenge. But this is all phase 1. And at the very beginning in the title slide, it's like, the why, the how, and the who cares. We've kind of talked about the how. We've kind of talked about who cares a little bit, but this is something that's really for anybody that's interested in IoT, obviously space in general. Any kind of RF stuff is definitely someone that's been really interesting. But the why to this we really haven't truly hit on. And as I said, I wanted to build something that I could hack. And once I had a platform, once I had the ability to run custom software and the hardware and stuff like that, the rest is just building out different scenarios and stuff. But in August of 2023, this past year, a gentleman named Johannes Wilbold, a PhD student out of Germany, did a presentation at Black Hat USA in Vegas, and where he essentially acquired hardware from the ESA, the European Space Agency, as well as a couple of other hardware components that were basically built as test beds for space. You bolt your stuff on and send it to space. And he identified just absolute glaring vulnerabilities, including the ability to update the firmware over the air, meaning any platform that was operational in space could be commandeered pretty easily. And ultimately, the statement that kind of stood out to me in this Register article was that the problem he opined was that space science is such a rarefied field that the developers just didn't have the cybersecurity skills to do a rigorous shakedown of a satellite in the first place. And that's the why. As a cybersecurity professional, I want to solve that problem. I want to be able to close that gap up. I want to be able to put myself in a position and others in a position that they can understand, they can have a conversation with the space guys as security guys and vice versa, because there is a huge language barrier. There's an understanding. I mean, the technical things that these individuals that work in space systems deal with on a daily basis is absolutely mind-blowing. I did a presentation at B-Side St. Louis back in October, and one of the individuals in the audience at the end of the Q&A, he informed me his sister worked in the accounting department of NASA. And if you remember, not too long ago, the International Space Station had a leak, an air leak in it that was attributed to the Russians, I believe. They accounted for the air that was lost down to the parts per billion, which is just an incredible thing to, if you think about it. Of course, that's the money side of things, but everybody within those organizations are accounting for things like that. And when you're having to design a system that has to operate on a very fixed power budget where every nano amp matters potentially to your mission being successful, it is very difficult to bolt on or to think about security when the whole idea is, does it work? Does it do the thing that I need it to do? I'm the perfect example of that. If you go back to the remote code execution vulnerability, it did exactly what I wanted to do. I needed to solve a problem. I solved the problem. Let's move on. I've had conversations with people in the industry that they go, well, is it flying? Yes. Okay, no problem. Like, we're not worried about it. Like, it's done. We can't touch it. We can't do anything about it. Like, we're not going to worry about it. And that is a problem that we're going to have to collectively work to improve. So one of my goals for this project initially was just to do it for myself and figure it out, but now it's gotten a lot broader. I'm actually working on a complete new set of hardware that will be you'll be able to buy as a kit, pre-made. You'll be able to run multiple different versions of software on it, not focusing on the RF side of stuff in the same way that AMSAT's CubeSat stuff is. Their stuff is incredible, and I support them completely. But from a cybersecurity perspective, there's a lot of things that we can do. There are a lot of platforms that we can look at. So this is running off a Raspberry Pi Zero, which has flown in space. CubeSat in 2022 was the actual first Raspberry Pi Zero to fly in space as the onboard computer. It completed its mission. It was absolutely awesome. And but things like more embedded system, STM32 stuff, FPGAs are definitely the name of the game in the commercial side of things, and being able to develop hardware platforms that people like me and you can go and just buy and then start playing with them without actually having, like, getting the hardware kind of abstracted out of the equation, going, here's all the stuff, here's how to get started, and things like that. I'm through my employer, I'm actively developing some training courses around one is an introduction to cybersecurity from a space perspective, and the other one's a little more hands-on hacking, where you actually use this type of hardware and the new version of hardware to go through simulated attacks, not just attacks but also detections from a defensive side of stuff. But that is here's some links here to the stuff that I recommend. For some reason, I put the same link in twice and stuff. But do you guys want to see it go for a little spin?
Well, yes.
All right, I'm going to stop sharing and then reshare. Let me get. So I unboxed these things 2 days ago because I coming home from South Dakota, I was like, I need to take a break.
Hey, Tim, we've got a question in the room.
Yep, fire away.
Hey, is there any way we ourselves can play with these boxes?
So yes and no. So currently the answer is technically no. But that is going to be changing very, very quickly. So one of the reasons that I went with LoRa specifically is because of the notion of LoRaWAN, which is a separate. It's kind of, you almost want to think of it like a sub system within the LoRa ecosystem. But it uses a system of gateways and network servers to be able to manage and broker information between IoT sensors using LoRa. So LoRa is the protocol, LoRaWAN is the implementation. And so the hardware's sitting right over there for me to start playing, getting set up next week, where I will actually expose an interface to the internet where you'll be able to send commands. It just be over. It's actually UDP, and it will hit the gateway, the LoRa gateway, and then broadcast the commands to the actual CubeSat. And then the CubeSat will process the data, send it back to the gateway, and then you'll be able to receive the output. And that's one of the reasons I went with LoRa specifically, because it gives me that capability of having online, offline kind of stuff. Also, I have it just got delayed in my efforts because I had to prioritize. But I have a digital twin. If you're not familiar with the concept of digital twin, it is just it's a simulation of all of the hardware that's in the CubeSat, with the exception of the camera, because I don't really know effective way to simulate a CubeSat. Although I did come up with the idea, I was like, I could just have it generate ASCII art for you, but I decided against that. But it effectively allowed you to go use the ground station, use the some of the stuff I'm about to display. It just takes all the radio part out of it, which is very important, like especially from a security perspective, considering a lot of this signals are not encrypted. You want to, but for going hands-on and stuff, getting initiated and stuff. So as soon as that stuff is ready, you guys will be the first ones I'll let know. I'm hoping the digital twin will be ready in like 2 weeks to kind of take for a test run and play with it. It'll have, like I said, 95% of the capabilities, and it'll have some of the same issues. It's like I'm in I forgot the name of the utility, but basically I'm throttling down the connection down to like 10 kilobits per second, and things like that, just to give you a little bit more of a real world. Another thing that nobody else knows about, so I'll let you guys know, if you're familiar with Oregon Trail, the game Oregon Trail, I grew up on it in elementary school. I'm building a version of Oregon Trail, but instead you are a ground state or a satellite operator for the day, and your satellite's under attack, and you've got to be able to make specific decisions to kind of teach you some of the fundamentals of the constraints, consider fundamentals of how satellites orientate themselves, and how and why you might want to do this versus this, like a simple way of like, how do you, if you have 6 solar panels on all 6 axes, how do you determine what direction the sun is? Well, you just look for the highest producing solar panel. or the combination of those two. But we don't necessarily think about that stuff. And like one of the things that I learned about this is here. Let me switch over.
Hey, Tim, we got another question.
All right, go ahead.
You mentioned that because of the way that the packets need to be so specifically laid out that the bandwidth had to be much stricter. How was is the actual structure of the packets publicly known, or was the structure actually?
So great question. So for my use case, the packets were I defined them myself, and it's not publicly known. I did that because of here again, I was trying to get to a milestone. In the future, there's a CCSDS, which, if you ask me what that stands for, it's the Consortium Consultative Space Directive Systems or something. It's basically a public group that has defined a bunch of protocols and provisions. They have what essentially a space packet protocol, and it defines a lot of the parameters for you. OpenC3 Cosmos has full support for that. You're still going to have to define out what all your packets are, and stuff like that. But in the real world, it's kind of, I would say it's a 50-50 shot as to whether they're using something like Space Packet Protocol or if they're using something proprietary. Universities and research organizations tend to be more proprietary because it's student-led in a lot of cases, lower budgets, time constraints, and things like that. Whereas more government-funded, larger organizations and stuff, they're going to fall under the standardization, such as Space Packet Protocol and stuff like that. Your large aerospace organizations and stuff, they're definitely going to be using that. There's also something called SpaceWire Protocol that's I haven't even really begun to touch on. So there is a standardization of this, but it's not standard across. Everybody uses it. Any other questions at the moment?
No, none.
All right, cool. I don't even know. Let's figure out what we're doing. All right, so I've just powered this thing up. So just give you a little. So this is what it looks like on the inside, and you guys kind of saw pictures and stuff. I only have solar panels on 5 axes. There's normally one here, but I took it off for the purpose of being able to show this. One of the things that just kind of baffled. So all of these solar panels are 150 milliamp, 5-volt, 150 milliamp power.
Hey, Tim?
Yep.
Since you're showing your camera, why don't you turn off the
screen share?
Yeah,
that works. So it's like, okay, I've got 6 axes at 150 milliamps times 5 volts. It's like, okay, this is what my power budget was. And then I started to quickly realize when we're orbiting, at any given time, only one solar panel is facing the Earth or facing the sun, which means it's getting maximum power. 1 or 2 solar panels will be getting some power from reflections off the atmosphere, and the other ones are going to be in complete darkness. So when you start doing the math, like best case scenario is like instead of a 6x on 150 milliamps, I'm like 1.25. And I was like, wow, that greatly changes my power budget considerably. And oh, by the way, I'm only in the sun once for half of an orbit, in low Earth orbit, approximately 93 minutes, depending on your inclination and your altitude, which means 46 and a half minutes I'm in complete darkness, not generating power. And these were things I'm like, oh, I've never had to consider that. It's like, when I'm hacking a network, I'm like, well, is their network switches going to be powered up right now? Yeah, they're going to be. But in satellite operations, especially in low Earth orbit, that may not always be the case. Let's see. So I've got my entire chronological history of failed PCBs. This is my favorite one. The one I finally actually got it to work. After hours and hours of staring at the schematic and the PCB, I still managed to cross the MOSI and the MISO pins for the SPI to the radio. And so my solution was just to cut those traces and jumper them. and it works. It absolutely. So it's going to go into the Hall of Fame. So here we've got the CubeSat up and running. I'm going to turn on my screen again because I've still got plenty of time. All right, so I'm going to run GQRX. If you'll see right here, you'll see this thing, and if you can look at the camera, you'll notice that about approximately every 10 seconds there will be a little blue LED light up. This is just indicating that a transmission has taken place, and so we can see that this packet has been sent. It's a chirp, is what it's called in the LoRa world, but from an SDR perspective, there's really no effective way of being able to read or demodulate it and see, because it is a proprietary thing. But we can at least see that information. If we go over here, and we're going to run this basic little Python script. I may have to reinitialize the modem. We'll see. Yep. Come on. All right, you want to be that way? All right, we'll give it a second, and we should get a welcome message. But of course, it's probably going to be like, yeah, I don't want to work now that we're doing a live demo.
Of course.
Yeah, that's always how it
That's pretty standard.
Come on. You just saw the packet. I know you did. Give it one more cycle. There we go. Okay, so for some reason it's the Circuit Python doesn't want to spit out the data correctly and stuff. So basically this here is the contents of the message that's being sent from the satellite with that beacon. So if we then do another command, God, don't run Python 2. So what we've actually done is here. I'll just show you real quick. It's pretty simple. All we're doing is we're sending a sat_debug command to the system. So actually, what I should have done is I missed one. Let's just do this. All right. Yeah. So, if you look at the bottom, it's hiding on my screen. There we go. It tells us that we should have use sat_debug. And if we do that, we get this list of commands and stuff like that. Most of these commands are implemented. Some of them I have actually blocked out. So we're going to jump to 4 real quick. So if we do sat ping, we can see that we sent a packet there. And
Wow. So,
it doesn't seem like the satellite's responding. There we go. All right, and we got a Pong. And so you'll notice here that we get this 0C. This is the telemetry packet ID that has been defined in the packet for Cosmos. And so if we were running this through Cosmos, which I'm not going to demonstrate tonight, because you kind of already saw the video, that's the identifier, because it's, hey, this packet is identified by this. Here's what the structure of it looks like. Here's how we handle this packet. If we run 3, and I'm going to pick this sucker up for a second and switch cameras, you probably won't see. Okay, we'll see. We'll see if this works. See if there's a red. Okay, so there's a little red light that just popped up. And so what we're actually doing is taking a picture of the satellite. And then now we are getting the packetized data from that satellite.
what does that even mean?
I have no idea how many packets this is. And so if you look over here in our waterfall, you can just see just lots and lots and lots and lots of packets coming through. And this is like the absolute best data rate you're realistically going to be able to get with this particular configuration of LoRa. And so if we look here, we now have a image file that was downloaded successfully. 6:34 this evening, which was just now. And let's see what happens. Hello, Lugs. And so we just took a picture of you guys all watching me, which is a little weird, but that's fine. And so that was a imagery transmission. A lot of people that I talked to that have worked with LoRa and understand this stuff, they go like, yeah, it's not really designed to do that. I'm like, I know, I bent it to my will to make it happen. And to overcome some of the shortfallings in terms of data reliability and things like that. But so that's just a basic demonstration of what kind of what we can do from a satellite perspective. Here, let's do 4 again. Just I don't even remember all the commands now. All right, so for instance, so here we have a command called get telemetry. In this case, it's returning a value here. We have the 6C, which is the telemetry ID. We're getting that it was an OK from the Arduino. It was indicating that. So we sent basically the way this transmission went is we went from the LoRa or from Python over serial to the through the Raspberry Pi Pico to the RFM 95. That got transmitted to the satellite, which then that LoRa module was connected to the onboard computer, which was then connected to the Arduino over UART. That was connected to 2 sensors, a BME 280, which is a pressure, humidity, and temperatures, an altitude sensor, and then a MPU 6050, which is a 6-axis IMU, specifically a 3-axis accelerometer and a 3-axis gyroscope, so that you can get relative orientation or absolute orientation of the satellite. So let's see if we do this again, and I'm going to rotate it real quick and see. So we can see that we've got different degrees of rotation and things like that. It gets a lot more complicated, the math on some of this stuff before being able to map this stuff out. The next iteration is actually going to use a BME, a BNO 055 from Bosch. It's a 9-axis. It includes a 3-axis magnetometer, but it has a built-in micro MCU that does what's called sensor fusion. And it basically takes all the raw data and does all the math for you so that you can either use Euler's angles or quaternions to be able to calculate change in orientations and angles, which is actually really, really complicated. But it's really cool because you can actually do it as a visualization. So it's like you could have, you could rotate the cube, and then your visualization software would rotate to match that both on angular velocity as well as the degrees of rotation. So there's a lot to this. This is literally phase 1 for how to hack a satellite, how to hack low Earth orbit. CubeSat, this was just the beginning. Had to get to this point to where I understood the systems, I understood the integrations, I understood what the limitations and the capabilities were, and then being able to expand upon that. So one of the things that I'm really excited about is if you look here, we're pretty much eating up the entire Z height of this CubeSat, which is internally is 83 millimeters. The next version hardware, I've got the first PCBs coming next week, which I'm just super, super excited. They're probably not going to work, but that's okay. It's an iterative process, and we're gonna learn. But I'm hoping to get the entire Z height under 50 millimeters. Which would allow us to have an expansion PCB available with SPI UART M I2C breakouts, so that you can actually add your own capabilities. What kind of capabilities would you like to add to this? I don't know. how about lasers? Optical communications is something that I've been playing around with. NASA's heavily invested in optical communications, been doing some super amazing research, especially for the Deep Space Network. But next year for Wild West Hacking Fest, the plan is to actually have 2 satellites with RF link to one of them, have a optical relay link between them two running PPP with IP over that. And then we're going to run a C2 channel, command and control like Metasploit, over that RF optical PPP link. And the only reason why is because we can. And that's really about all I've got. I've got just a couple minutes before I unfortunately do have to drop. And so, are there any questions, comments, or only positive feedback?
We got a question here. Go ahead.
Well, I have one about, have you tried to hack it yet? And if you were successful, do you plan on keeping those vulnerabilities active so other people can attempt to find them?
Yeah. So have I hacked it? Yes. Are those vulnerabilities going to be remain public? Yes and no. The design right now, most of them have been patched. But the plan is to actually strategically re-add those back in once everything is working as I need to. So the first thing was just getting the basis of it working and stuff. But fundamentally, yes, introducing the kind of next step from a software perspective is actually introducing the vulnerabilities and things like that. So one of the big vulnerabilities, it actually stems from RF, is the fact that things aren't encrypted. Oftentimes, it's not for obvious reasons, but the number one reason is because of, fundamentally is radiation. The fact that if you have experienced a bit flip in memory where your encryption key is, and you don't have a means of falling back to unencrypted comms, you've now lost your satellite. So at a minimum, every satellite falls back to open comms at some point. Hopefully, the only kind of options that are available to you during that state is to reestablish encrypted comms, but that's not always the case. So some of the RF stuff will be a little bit more difficult to kind of simulate, but AMSAT, they are Alan and them are working on a new version of the CubeSat simulator that has 2 radios that will be able to do send and receive. And so I plan to also incorporate that into the overall kind of training and the platform as well to be able to showcase some of that being able to demodulate the actual packets and stuff, which they do a great job with their Fox Term Ground Station and stuff like that, which is fantastic. But just being add on this kind of offensive security capability and stuff like that. Vulnerabilities such as obviously within the software, code execution, command fuzzing, replay attacks, but then also getting into resource constraints and stuff, like being able like, hey, can I just send like a photo command like over and over and over and over again, which will cause it to use the power to take the picture, and then B, transmit that data. And you can do that. You could literally just put my Python script in a loop, and it will drain the battery faster than it can actually generate. Well, if I was sitting outside, the sun produces more than enough power to actually maintain operational state, but in orbit, it wouldn't. Within 40, once the power drains, I'm 1/2 orbit away from dying. And then it's a matter of, can I reboot? Can I recharge? Can I, there's a lot of different kind of steps and abusing state changes is something else that I'm definitely wanting to be able to showcase. Like if we can force the satellite into a non-nominal state, is there a way that we can keep it there? The ability to upgrade firmware on the fly, pun intended, is also something that will be demonstrated as well. And that has been done historically. Johannes Vilbold showed that it was possible with the ESA hardware back in August of this year. And those are just some of the vulnerability and attack paths that I'm going to be showcasing. A lot of this is going to be, like I said, going to be covered in a training course that I'm going to be actively developing. But access to this and stuff will that's going to be like the taught version. Everything in most cases moving forward is going to be released at some level open source so that you can do it yourself, including Gerber files and everything like that, so that you can go and order the PCBs yourself.
We got another question here.
Yes.
I know you. How do we build this ourselves if we wanted to?
So if you want to build this yourselves, I will send the slides out, or I'll send them to you, Jace. But I'm going to let me share my screen again. Share. I just lost. This link here, this GitHub, is where you want to be. Let me see if I can get it to pull up or copy.
CubeSat.
Yep.
L&B Johnson.
I'll send it. I'll send in a follow-up email. I'll just reply back, Jace, to the email for this meeting and stuff. But that's your cost right now is probably going to be around $300 to $350, depending on how you want. That's not how much I have in mind and stuff, but it's because of the cost of research and stuff like that. My ultimate goal is to actually get one under $200 that has 95% of the capability, so that like if you don't want to build one, you don't have to. You just go like literally just assemble it like Lego blocks. You'll stack the PCBs, attach the put it in the 3D printed frame, and install the software, and you're off to the races.
What about the smaller things that you built?
Oh, these? Yeah, so the design files for those have not. I haven't released those yet, but those will be released as well.
Okay.
And if anybody wants it, it's. I mean, you don't have to go this solution. The reason why I went with this solution is because like you can use something like from Adafruit. They already have feathers that does this, but they're $35 a piece. Whereas if I got these, cost me like $11 and some odd cents to make, and so even if I sold them pre-made, $20, you're still saving $15 or something like that. So I will release the design files, but also I'm probably gonna just have some that you could just buy as well.
I got one last question.
Once you have the digital twin up and running, what would be the reporting process for new CVEs?
I don't. Just email me. I know. I actually haven't thought about that. And so yeah, I'd probably just. So what I would do is where it is going to be hosted. I'd set up a security.txt that will have all the information. It's like, hey, if you find something that's not, one of these intended vulnerabilities and stuff, because like if you go through the documentation, like it's like, hey, here's this type of vulnerability, here's what we're looking for and stuff like that. But if it's anything outside of that, then yeah, I would set up an email box that would be identified in the security.txt file.
Thank you. I think
Awesome.
this is your hard stop, right, Tim?
Yep.
Oh, Ben has a question.
No, I don't. I was just trying to clap.
Oh, thank you so much, Tim.
Thank you, everyone. And if you guys have any questions or anything like that, just like I'm subscribed to the email group or whatever for
To the mailing list.
Yeah, to the mailing. Good. I couldn't think about that.
Yes.
And so yeah, just email me. We'll keep the conversation going. I've had to shift gears a lot. Once we got through Wild West Hacking Fest, I was like, okay, take a little bit break, and now we're into full ramp up mode. I'm hoping to have all the new hardware available in April. That you'll be able to actually buy, a second kit or a new kit or build your own and stuff. But that's, some of that stuff just takes time. It's a 3-year roadmap moving forward as far as what the iterations are going to be. We're going to be changed. So version 2 is still going to be Raspberry Pi Zero based. Version 3 is going to be RP 2040 based, which will allow us to do C, C++, Arduino, Micro, and Circuit Python, as well as free RTOS. Because once you get into the real-time operating systems, that's where things really start to get real in terms of what's actually flying. So,
Thank
any
you.
other questions?
I think we're all mind blown right here. At least I am.
Yeah, well, thank you guys for having me. Thank you for the sponsors. I'm not there to enjoy the meal and stuff, but thank you for the support for the group. Like I said, I kind of grew up in my career with these guys back in 2011, 2012, going to the Linux Fest and being a part of this group and stuff. So it's thank you for the support for them, and I hope you guys have a great time.
Thanks a lot, Tim.
All right, have a good one.
Good night.